Good morning, everyone. I'm going to talk about the Ginzburg-Landau theory in the framework of 2D crossfields. So I won't talk at all about 3D frame fields, and actually be more about the planar settings. And if I decided to talk about Ginzburg-Landau theory, it's because it could interest some of you. Apparently, it has become trendy among the mesh community, so the functional of Ginzburg-Landau has become trendy lately. There were some papers and research notes about it. But before giving you the Ginzburg-Landau secrets, I have to warn you about the thing, is that size matters for crossfields. So we will see how it is related to Ginzburg-Landau theory. But before giving you the details, I just want to give you a feeling about it with those two pictures. So on the left one, you have an analysis which is perfectly a mesh with regular triangulation. So we don't have any irregular vertices. And on the right, you have a square which has been meshed such that you double the number of elements from top to bottom. So in the case of the last picture, so with the analysis, we see that the quadrangles don't have the same shape, despite the fact that it is regular. And on the right, we see that we had to add two irregular vertices in order to satisfy the requirement, which was to double the number of elements from top to bottom. So we see that size will be an important feature for the crossfield computation. Okay, so let's review quickly the functional. I guess that that in the next talk we will have also a reviewing of this functional. So I'm not going to spend a lot of time on it. So basically, the Ginzburg-Landau functional is about to minimize the Dirichlet energy of the mapping corresponding to a cross. But if you enforce the constraint in every point of your domain, it's not going to work well because of the topological constraints that are related to the Euler-Poincaré characteristic. So you have to relax this constraint, but if you relax it, the crossfield that you are going to get won't comply with a full quadrangular mesh. So an engineer approach is to penalize those crossfields with a penalty term that foster mapping that correspond to a cross, and doing so we ends up with a nice crossfield. So basically, the functional is easy to understand, but that's not what is important in this talk. What is important is that when you are going to minimize this energy, it corresponds to some expression when epsilon tends towards 0. And this expression is this one, and I'm going to give you a short description about each term. But at the moment, I'm going to ignore the first term. We will see what it means later. Just keep in mind that there is a function phi, which will be very important for our theory about the Ginzburg-Landau. So basically, the first term between the brackets, when you are going to minimize the Ginzburg-Landau functional, you are going to ask for indices so that the indices of the critical points of the singularities have to be plus or minus 1. The second term, if you have critical points which have the same sign of indices, you are going to ask them to be as far as possible of each other. But if you look at the above picture, you will see that, okay, they are far from each other, but they are not the furthest possible. So the furthest possible would be on the boundary. And it's because of the last term that is not the case, because this term, even if the name is related to the sanitary situation, it's quite independent. This is a confinement energy. So it means that it prevents the critical points to lay on the boundary. with this function R. And so keep in mind that we have two functions to give later some description, the phi function and the R function. Okay, so now that I have this energy, I could play with it, and I could minimize it in some cases. So here I'm going to minimize it for ellipses with three kinds of configuration for the critical points. So in the configuration would be to put by critical point in a rectangular configuration, or in a parallelogram configuration, or align along the main axis of my ellipse. And I could compare at each time for each kind of configuration. I compute the best occurrence, so the one that is going to minimize my energy, and I may compare it with the other configuration and check how it behaves depending on the eccentricity of the ellipse. So we see that the parallelogram configuration is going to be all the time the best one, okay? But that's not what I wanted to show you here. I'm sure that you sleep well at night without thinking about the best configuration of critical points within an ellipsis. But it's to give you some insight about the R and phi function. So you see that there are some gray isolines here. Those gray isolines represent the level set of the phi function. And we may see where the critical points are when those isolines are quite close to each other. So we see the corresponding configuration in the tree animation. And then you have some fill isocontours, so where you have colors. Those fill isocontours represent the R function. And where those isocontours are black, that's where the R function is negative. And if we look back at the previous expression, we see that the R function, there is a minus m. And so when R is going to be negative, we are going to increase this energy. So we don't want to have critical points where R is negative. And beyond that, in the case of the align configuration, we may see that where R is negative is going to switch at some point, and that's why we see that the energy is decreasing when the eccentricity of the ellipse increases. Okay, but I was able to compute it, so it means that I have some definition for the phi function and the R function. So basically the R function is only the regular part of the phi function, so it means if I know phi, I know R by definition. So let's focus on the left part of my slides where I have the definition of the phi function, and we see it's given by Poisson problem with a Neumann boundary condition. And since this problem only gives this description of phi thanks to its derivative, we need to add an extra condition in order to ensure the uniqueness of the phi function. Okay, but we still don't know what is phi. It satisfies a problem, okay, but what is it? Actually, we may see phi as the dual function of the crossfit because it satisfies the same topological constraint. So if we look at the Poisson problem, and we remember a smooth version of the Gauss-Bonnet theorem, and that will represent the Poisson problem in a conservative form, we may see that we are going to satisfy the topological constraint because we recover this term. But still, we don't know what is it exactly. Okay, it is a dual function of our Ginzburg-Landau functional, but what does it represent? So we need to work out a bit the boundary condition in our case, and we are going to extend it within the full domain, or at least almost everywhere, because we are going to perforate to dig hole in our domain around the critical points. So the critical points are not there anymore, and it's not you are not going to break the topological constraint since you change the topology of your domain. And so you extend this boundary condition into the perforated domain. And actually this expression, as you may see here, it is the tangential derivative of theta, of the orientation of your cross. Then the left expression is somehow the gradient of theta. And here we have the gradient of phi, but which is expressed in an orthogonal way. So it means that the gradient of theta is orthogonal to the gradient of phi. Okay, but still, we don't know what it is exactly in our case. So we need to use a differential geometry tool, which is the Lie bracket. And we are going to use it to finally find out what is phi. So basically the Lie bracket tells you if a two vector field comes from coordinate system. So in other words, if you integrate those two vector fields, are you going to get parametrization? And it is the case if this quantity is zero, and this quantity is represented here. So if this vector is the zero vector, it means that the vector field u and v that this vector field correspond to a coordinate system. And so we are going to compute this quantity in the case of a cross field. So we take two orthogonal directions and we compute it. We compute this Lie bracket, but we end up with this quantity, so the gradient of theta, which is non-zero except if theta is trivial, is constant. So in the case of a square, your cross field is aligned the same way at every point. So that's the only way to have a zero Lie bracket. But we are not interested in this situation, but it's not a big deal. It doesn't mean that you have to throw away your cross field. You just need to do something. And for example, you could decide to scale it with some h function. So in other words, you are going to ask what is the size of your quadrangles among such that your cross field becomes integrable in some sense. And so you do it. You want to avoid this quantity here, and doing so you end up with those equations. And if you look carefully to this expression, you see that again we have something which tells us that the gradient of theta has to be orthogonal to the gradient of the logarithm of the size of your mesh. So if you remember on the last slide, it has to be orthogonal to the gradient of the phi function. So it means that the phi function is somehow related to the logarithm of the size field that you should use in order to have a perfect quadrangular mesh. At this point, you could ask yourself, okay, but I don't want to use the Lie bracket. I've heard about the integrability condition. Yes, in the planar settings, you may use it, and you would end up with the same condition for the gradient of theta and the size field. Okay, but still, there is some question about this expression. Where does it come from? So I'm going to just summarize the key step to get it, but everything is in the book of Betulay. So basically, you know that the gradient of your cross field corresponds to the gradient of the phi function, and because of those expressions. So we know that. We are going to use the divergence theorem in order to expand this expression, and so we do it. And remember, we work on the perforated domain, so we end up with this expression, and we have with this term, and we have to expand it also. So we are going to do that to expand this term, and to do that, we are going to use an auxiliary function, which is actually very important. So the function Si is the harmonic part of phi in the neighborhood of the corresponding critical point. And since it's harmonic in the neighborhood of the critical point, you know that it's going to be 0 there. And also you may use the mean value property of harmonic function. And at the end, you know that the gradient of your function is going to be bounded by some constant. And thanks to that, when you are going to shrink your course, when you are going to, when the radius of your hole is going to tend towards 0, you are going to end up with this quantity, and that's how you end up with this expression where you may see that corresponds to the one that we had here. And yes, it does correspond, even if we have different terms for those one. It's because remember that R is the regular part of the phi function, while Si is only regular in the neighborhood. So you have to withdraw this quantity from S in order to get R. At some point, we have seen that we had a term that was telling us that all the indices of our critical point has to be plus or minus 1, but you could ask for crossfield with higher order indices. It could be useful. So instead of so we work with a smaller expression here. We just so we don't have the term about the unit indices. And what is interesting with this expression is that if you want to minimize it, you have an exact expression for its gradient depending on the location of your critical points. And actually, to compute this, it's really a tiny cost, because since this is the harmonic part of phi in the neighborhood of the corresponding critical point, you just have to solve a tiny homogeneous Laplace equation there, and you are able to compute the gradient of this function, and so you know how to optimize your crossfield based on the critical point. So here, just a dummy demonstration. Here, what I have done is that I have computed the perforated Dirac energy of the phi function. So for a set for configuration of critical points, and I'm testing each neighbor vertices of critical point in order to decrease this perforated Dirac energy. But you see also that there is a kind of RO, and this RO is the gradient of this energy that I have just shown you, and we may see that the displacement of the critical point is kind of consistent with this greedy approach. So it's time for me to conclude. So remember, size matters for crossfield. So in the case of our square where we wanted to double the number of elements from top to bottom, we see that we have to introduce at least 2 critical points in order to create some gradient in the size field. Avoiding the bracket is crucial. Actually, I think that that's a concern that everyone in this workshop should have when we deal with when we want to quadrangulate a surface. But I have shown you how to do that with some scaling, so with a kind of size mesh. But actually, it's not the only approach. You could do that by breaking the orthogonality of your crossfield with some phase angle. So it's something that actually has been done in a paper, so with the title Chebychev nets. And they are avoiding the Lie bracket by breaking the orthogonality. And but they don't derive this expression because they are doing another way. But if you do the math in the case of the planar settings, you end up with this expression, which is less simple than the one we got with the scaling, so with the size mesh. Okay, I have told you that we could have a simpler energy in order to optimize the crossfield based on the critical point. And its gradient was really cheap to compute, and actually if you want to do it efficiently, you should do it in a parallel way, because it's embarrassingly parallel. And the last thing to keep in mind is that everything has been done in the planar settings, which means that we have to account for the Gaussian curvature if we want to work on curved surfaces, and so we should derive the same mathematical expression in order to see what happens. And also we could ask our crossfield to fit with a target size map, and so also we should do the math the same way in order to see what happens with this expression. So I know that maybe I'm certainly been too fast for it, but please don't hesitate to ask questions just after this, or in the chat. I will be very happy if I got the interest of anyone. So thank you for your attention.
Thank you, Pierre-Alexandre. If there are any questions, don't hesitate. I can ask one, waiting for the others. So you show the link between the kind of size map and your crossfield. Can you inverse this problem? Like starting from a size map, is it possible to find a crossfield and some singularities to have this scaling matching the size map?
So it's on the to-do list if one day I resume this work, because I'm not working on that anymore at the moment. So actually we should derive the corresponding expression of this quantity, which is the runnerized energy in the case of a target size map. But the thing is that in that case you have to add extra pair of singularities. So there we have opposite, we have critical points whose indices are opposite, and it may appear suboptimal, but actually you don't have the choice if you want to have a crossfield which fits with a given size map. And so it means that somehow you should be able to add those critical points. So you could do it in a heuristical way, but mathematically you could have some interest in the emergence of singularities. But for the latter possibility, it means that you have to deal with measure theory, which is not that easy to optimize, at least from my experience. So I have tried that during the last semester, and I didn't manage to have something working. So yes, theoretically it seems possible, but computationally it's a challenge, I would say, at least for me.
Okay, thank you. Are there other questions? No, so we'll go to the next talk. Don't hesitate to ask a question in Discord.
Sorry, I have one question before you go.
Oh, okay.
Yeah, thanks for the nice talk. So do you see any chance to generalize these the analysis also to general crossfields, so something with anisotropic scaling or maybe even non-orthogonality?
That's a good question. I guess it should be possible, but the math. So I've tried that, but the math are much more complicated. I think it's possible, but to end up, in order to end up with something which is as neat as we have in the case of just orthogonal crossfield and one scaling, I fear, I think that we won't have something usable. For something where you break the orthogonality, that you scale two direction in an independent way, I don't have the feeling that we are going to have something usable for an algorithm. So I think that the theory has some limits for application, at least. So that's my feeling.
Yeah, thanks for the answer. So maybe one way you could approach that is by kind of splitting the field into having a separate metric and then something that is orthogonal and uniform scaling in this metric, and then also have a kind of alternating optimization scheme or so on.
Yes.
I didn't think in detail about it, but I'm just guessing.
Yes, I mean, we could split the program in several steps and do it in an iterative way. So compute a crossfield, see how the corresponding scaling is, and then penalize it. So we could have such approach, but I don't know how it's going to behave. And the thing is that you are using part of the theory in order to have something that meets with your expectation, but it's a bit beyond the theory, I would say, what we expect at least from there. But it's worth trying at least.